Okay, yesterday I started chapter 3 and I got through like the first 10 slides. I'm just going to kind of fly through those again just to kind of remind you where we're at. And today's lecture is going to be more of a philosophical type lecture than it's going to be getting into really the technical aspects of what's going on. But let me just kind of go through it and right there and slide through right here. So this is our chapter 3, and this is where we start talking about structured programming development. And chapters 1 and 2, we kind of learned a little bit of what microprocessors are and the background of digital logic and that there. We looked at the different types of programming languages and things like that. We learned a little bit in the last week or so on the computer software we're using, although these two young ladies, we discovered that their computers don't like the software, so they have to find other computers when we do labs that they're, or maybe they might work this time, I don't know. But it seems like these computers have different versions of the Div C on that there. But regardless, we saw how we write computer programs. That there. This chapter here starts off with this section here called told you I was right there. That there. We're going to start off with basic problem solving techniques right there. And that there. Well, I'll survive that there. And then we're going to go through this design process called top-down stepwise refinement. Now, these two things right there are not defined to computer programming. You know, that's the key thing we have to keep in mind is that when we look at basic problem-solving techniques, that is, and we'll repeat this same section because the same section is part of the MATLAB lectures that I'll use. But, well, we have problems all the way through life, and I mentioned that what engineers do more than anything else is they solve problems. That there. Now, we've got a class of engineers that are research engineers and design engineers, and they're working on the next generation iPhone, iPad, but 90% of the engineering work, even in the design world, is trying to fix problems. And I mentioned the problem with the Note 7 exploding. You know, that was a problem that the engineers had to go back and look at the design and look at the manufacturing process and find out why these phones exploded in certain conditions. And as engineers, we work on projects and on products that sometimes have life and death repercussions. If we don't do our jobs correctly as an engineer, sometimes people die. That's just a fact of life. That there. If you're working in the medical electronics area and you're designing pacemakers that go into somebody's chest to keep their heart beating at a certain rate, and your design malfunctions, what happens to the person wearing the pacemaker? That there. Not good things. If you're the person who's designing the controller that controls a jet aircraft on a Boeing 737, and your design is a poor design, what happens to the people flying on that aircraft? Right there. What happens if you do a design and you fail to take into account what happens when a flock of birds flies into the engine of that aircraft? Which has happened. If anybody's ever watched the movie, I can't remember the title of it, something, where the aircraft lands in the Hudson River after taking off from JFK Airport. What's that? Yeah, the Sully story, Captain Sully, that there. And that's what caused that malfunction, was a flock of birds flew into the engine upon takeoff, and the engines failed. That there. Well, that's an engineering problem, that there, because somehow that engine has to be designed in a way that it can withstand 100 birds flying into the turbine and not shut down. Because in this particular case, nobody died, but a multi-million-dollar airplane found itself at the bottom of the river. Or I don't know, they may have pulled it out. I didn't follow the story, but obviously, a lot of luggage was damaged and lost in the cargo hold, and there was a lot of, even though nobody died, a lot of bad things did happen out there. So engineers not only have to solve problems, they also have to anticipate problems. You have to anticipate when things go wrong. You're designing a self-driving automobile. This is one of the newest technologies out there, and it's going to become reality. Self-driving vehicles are going to become the norm in the next 10 to 20 years. And what happens if you've got some clown, and it might be me, running around on a motorcycle or a scooter that runs a red light, and you have a self-driving car? All of a sudden this vehicle shoots across it. It's not supposed to be in the road. They have a red light, but anybody who's been in Malaysia more than 10 minutes realize that, especially motorcycle drivers don't necessarily follow traffic signals, right? That there. So that creates problems for someone designing the software for a self-driving automobile, is that you will always have, even though, let's say 10 years from now, the technology of self-driving cars progresses so far, so quickly, that you can't buy a car with a steering wheel anymore. The steering wheel has disappeared. It's not even there. Because the car drives itself right there. You're seeing that a lot with transmissions. It's getting harder and harder to buy a car with a manual transmission in many Western countries. Malaysia, it's still common. I mean, you can go buy a Myvi with a 4 or 5-speed transmission. But in the United States, for example, you can't go buy a Honda Civic or a Nissan Sentra or a Buick LeSabre or any of the cars sold in the United States and find a clutch and a manual transmission. They just don't sell them. Nobody buys them. You can't get them out there. So you getting back to this point, we're going to be talking about problem-solving techniques that there. And this is not, as I said, I'm talking about this as if I could teach you how to do this. If I could teach everybody in this room how to be a great problem solver, I would be the best faculty member that UniKL could ever hire that there, or Purdue University could have ever hired. But the truth of the matter is, this is a skill that you develop through trial and error and practice. The only thing I can do here as a lecturer is tell you that 80% of the work I did as an engineer working out in industry was solving problems. That there, coming up with solutions. I spent 5 years as a head of, department chair, that there, and that was a management role. I probably spent 90% of my time solving problems. And a lot of times these problems were not technical problems. They were, this person said this and this person didn't like that, and this person doesn't like women. This woman doesn't like men looking at her, but yet she dresses a certain way. I mean, you name it, I had those kinds of problems that there. this professor didn't like to have students in his class that weren't upper level students, so he would want to put 600 prerequisites in the course, and I'd have to deal with, how to get him to accept the fact that, you have to have sophomores in your course because that's where it fits into the program out there. So, but again, problem solving is not unique to engineering. You raise children. Children don't necessarily do what you tell them to do, right? You remember back, well, some of you don't remember back very far. You probably didn't do what your parents told you to do all the time, right? One of the challenges for your parents might have been to get you to accept the idea of going to college versus sitting around and playing video games or chit-chatting on Facebook. Or nobody chit-chats on Facebook now. Was it Instagram and WhatsApp are the main? Are those still the two? Are those the main chatting? What? Or is there something else out now? WhatsApp was the big one a year ago. Out there, I can't keep up with them. I'm one of these old style people that like to use telephones to hold up to my ear and talk to the person. Actually, now that I've had the stroke, my arm gets tired, so I use a headset out there. So, I'm not a chatter with phones, and I don't do the 2-finger out there. So, how do we solve problems? We're going to develop algorithms through a top-down, stepwise refinement. Now, again, I'm talking a lot to the list of topics, but we'll go through that there. An algorithm is a way of doing something. It's a recipe. It's a set of steps. Now, the way we solve problems typically is we break them up into smaller problems, and we solve the smaller problems, and we connect those to the bigger picture. If we're going to bake a cake, we have to mix the dry ingredients, then we have to mix the wet ingredients that's there. If we're going to rebuild an engine, we're going to have to take it out of the car first. That involves a number of steps. We break it up into a series of smaller steps. Now, sometimes in problem solving, our biggest problem is figuring out what our problem is. That there, but we will talk about that. Then we'll get back to the technical part where we talk about the if-then and the if-else and the while and counters that there. So we're going to but today I probably won't get much beyond the problem solving discussion. I might get to the if-else. Okay, skip that there. All right, I went through the slide earlier. This is worth repeating. Before you write any program, you have to understand what the problem is. Now, a lot of times when you're going to develop a program to do something, you have to talk to people. You have to look at how they're doing things without the computer program in order to figure out the steps involved. There. If you're going to write a program for a restaurant, I'll use that as an example. My wife and I and my sister went last night to this little mama restaurant near our house, and it's all computerized. They've got a series of tables, and they've got, every time you do an order, they go and hit your table number, and they put in what item you're ordering, and it keeps track of your bill. I've seen some of those, they've got the little cards that they play on your table, and they add to your, they keep that there. Other places I go to have a scrap of paper for each table. That there. And then when you go to check out, they go through the stack of papers and try to figure out which one's yours. And then they pull out the handheld calculator. They calculate your bill. But if you're going to write the program for the restaurant that I went at last night where they keep track of the tables, you probably would go and look at how that restaurant operates without a computer. And then you design a computer program to simulate the same steps. The steps is like a customer sits at a table. So you have to have your tables numbered in a way that you can identify what bill goes with what customer. I've been to restaurants that don't have computerized systems, and I've had waiters walk up to me with a tray full of food that doesn't look anything like what I ordered, and come to find out that the tray was for the table next to me because they weren't using table numbers as part of the order that there. So when the first the one person that comes to my table and if they're coming to my table and I'm by myself, it's probably the only person who speaks English that there because my Malay isn't that good, but then there's usually other people that work at the restaurant that actually run the food from the kitchen to the tables. And without that table number guide, I've had them go to 3 or 4 tables with the order trying to figure out whose food is this. And I hate to say it, there's been a few times that the food has come to me, I look at the food, I say, well, that doesn't look quite like nasi goreng kampung, but I guess that's the way they make it here. And their teo ice, it's got a lemon in it, and I ordered just teo ice. They screwed up in the kitchen. I eat that, and then 5 minutes later, the table next to me gets my order and goes, well, this doesn't look like nasi goreng China. And where's the lemon in my teo ice lemao? That there. I mean, I've done that, and I think everyone knows of that. Probably I'm probably not the only one in this room who's done that. Is eating the wrong order and just figured, man, the chef just doesn't know how to cook this the right way or whatever. Come to find out, it's the wrong order. Out there. Well, so before we start writing the problem, the program, we have to understand what the program is supposed to do. That there, and we'll get into more detail. But we have to plan out what this program is going to do. Now, sometimes these programs do things such as play video games. Now, video games are very elaborate computer programs. They draw very intricate graphics on there. They simulate gunfights or dragon fights or whatever game it is. I'm not a gamer. My niece's husband actually does do hand paintings that then become computer graphics for video games. So he works in the video game industry. I don't know him very well. I mean, they just got married a few weeks ago out there. But the whole thing is that I've been around the computer gaming industry, and that's actually a very, very lucrative business today. A lot of the guys seem to be more into the gaming than the ladies. I don't know. Is that probably true? Are any of you 3 ladies computer gamers? Do you sit there and fight dragons and kill? Go into knights. I don't know what other games are there. There's the gunfights. I mean, World War II. The spaceships. And my children went through the gaming phase. They kind of outgrew the gaming phase. But that's different type of programming. I don't teach computer gaming programming. I don't know anything about computer gaming program, nor could I care less. That there, to me, spending 6 hours of a day playing a computer game is, 6 hours. But I'll spend 6 hours reading a book. So that there, that there. But regardless, you have to understand what your program is supposed to do. So your program can be making bread, and believe it or not, you can write a computer program. I've done it. That actually makes bread. Now it controls the mixer and the weight of the flour that's going into it, the amount of milk that's coming in. We're controlling hardware, but we're writing a computer program that is going to make bread. Now, we don't do that for our own personal kitchens because we don't have a big industrial assembly line for making bread. But there are computer programs out there, and I'm sure if you're to go to Gardenia out in Shalom, that there, I've been in their plant a few times, and you'll see the industrial equipment and the computer program that's run by computer programs that make your bread. There's computer programs that will manufacture a car step by step. Of course, this is industrial automation right there. What we're going to be talking about here are desktop applications where our inputs are things we type from the keyboard or from a file, and our outputs are things we can see on the screen or to a file right there. And most of the programs we're going to be talking about here are either going to be solving mathematical equations or running a restaurant type thing where we do billing just to get some practice out there. But we have to understand what our problems is. That's it. So, an algorithm, again, I talked about this, is the fancy word for the recipe, a procedure in solving this. An algorithm is basically the list of steps in which we do something, right there. And of course, we talked about the rise and shine algorithm of if this gets out of order, our executive takes his shower after he puts his clothes on, and as a result, he shows up to work soaking wet, right there. I mean, the order in which we follow our procedures is very important. Doing something out of order is not always good. And certain things, especially in, for example, if you're placing a head gasket on a car, you may have to leave the gasket cement or seal that they're, depending on how you do that. I always had warped heads, so I used a lot of stuff called permabond that fills in there. So it fills it, but you got to let the cement dry before you start trying to move the engine into the car. If you're baking bread, sometimes you have to leave the dough rise in order to have airy bread, right there. So some of our steps in our algorithms may be wait for something to happen out there. If we're writing a program that controls a robotic arm and we tell it to move from point A to point B, and it takes 4 seconds for that to happen, then we have to put that 4-second delay in there. So it's that there. So we have to specify the order in which they're there. I mentioned this before. This is close where we ended up. Pseudocode is not really code. The word pseudo means not quite. A Battalion Street Rolex is a pseudo Rolex. In other words, it's not really a Rolex. It says Rolex. It looks like a Rolex. Even keeps time sometimes like a Rolex. But it's definitely not a Rolex, right? It's a pseudo Rolex right there. Pseudocode is an artificial informal language that helps you develop an algorithm. In other words, you sit down and you write down the steps it takes to do something. Mamak Program 101 is waiter walks over to table, takes order. Step number 2, waiter enters order into computer. Step number 3, computer screen in kitchen shows cook which items have been ordered. Step number 4, cook prepares food. Now, of course, there's an algorithm for the cook to prepare the food. They're supposed to follow certain recipes. Next item, cook places order on counter with a little ticket to tell the food runner, what table it goes to. Next step, food delivered to table. Next step, wait for customer to eat the food. Then clear the dishes, present bill to customer, and then collect bill and give receipt. These are the things that happen at a restaurant. All right. Now, did I cover exactly how each one is done? No. But I got kind of an idea what has to happen in my software. Some of these steps are done by a computer. That the bill is calculated by the computer. The order is transmitted from the main terminal to the kitchen. The kitchen has a monitor that tells the cook what to cook. The computer also tells the waiter which table the order is supposed to go to. Right there. The bill is calculated and the amount of change is all done by the computer. But the computer doesn't cook the food in your typical restaurant, right? You have a person in the restaurant that cooks the food. The computer doesn't take the food to the table. That is done by a person, right there. The change is not necessarily distributed by the computer. That's done by a person standing at the cash register. Now that varies. Now there are restaurants that I've been to, I haven't seen them in Malaysia, where you sit down at your table, and on your table there's an iPad that's mounted on a little circle thing right there. And you go through it on the iPad as your recipe, and you enter on the iPad what you want. Right there. So the waiter is no longer there. There's nobody coming to your table to take your order. Right there. And then the order goes straight from your table to the kitchen. It's cooked. Someone from the kitchen will bring it out. And even now, I've seen them some places where a little beep pops up on your iPad and it tells you to go over to the counter and get your food. They've eliminated the waiter or waitress completely. You go get your food at the counter and bring it to your table. And then when you're all done eating, tells you what your bill is, you pull out your credit card and swipe it on the iPad there, and you have never seen a person the entire time you sat at the restaurant that works there. Completely gone. That's there. So Amazon has got a new store that they just opened in Seattle that you walk in with your shopping cart and you fill it up as you go through the store with whether you want to buy. As you go through the store, it scans your little membership card, which is attached to your checking account, your current account. Keeps track of it. The software in the store, through various cameras and sensors and everything else, keeps track of what's in your shopping cart, what you put in your cart, what you take out. Right there. RFID tags, radio frequency identification tags, are on many units. So when you're done in the store, you just walk out. You don't see a person. There's no cashier in the process. You just walk out of the store and you put the items in your car and push the cart back to the front of the store. That's there. No people involved. Right there. Again, we're getting into the world of compute. A computer program has to keep track of all that there. We write pseudocode. As I said, today was a day where I'm just kind of getting off on soapboxes, talking about different subjects. But that is a movement in a lot of the Western world, is to eliminate the lower class workers. Right there. There are McDonald's in various countries where, again, you walk up to the counter and you push into an iPad or a similar unit what your order is. You don't have somebody that takes your order. So again, we're looking at computer programs here that are doing things that we think of people doing. A pseudocode, getting back to my slides, and I'm almost completely, slides is plugged in. There is, this slide says is similar to everyday English. You can write pseudocode in whatever language you want. If Mandarin is your language of thinking, then you use Mandarin. If Malay is your language that you use Malay. If it's English. That there. But you write it in a series of steps that make sense to you. Now you do this in a way that, and this is experience that you can easily translate it over to a programming language. Now pseudocode for a C program is going to look very much like pseudocode for a Pascal or a Fortran program. What are the steps required for this program to do its thing? Right there. You'll see this diagram from time to time where I've got a little box here. I have inputs here. Now the inputs can come from hardware sources, they can come from keyboards, they can come from sensors, they can come from anywhere. And then we have outputs. And in here we have our computer program right there. So this is what a typical model of what a computer program system looks like. We have inputs, and inputs can come from all kinds of places. If you're looking at a satellite system that's out in space, the inputs might be signals that are coming from Earth, that they're telling the satellite to turn a certain direction or move to a certain location. The outputs might be servo motors that turn various jet engines or engines that they may turn things such as flaps or deflectors. Our inputs might be something, the accelerator on the floor of your car might be an input to a computer program, and the computer program receives the signal from the accelerator pump, and then the output is the position of the gasoline valve that controls how much fuel that's going through the fuel injectors that drive the engine of the car. So our inputs might be a series of 3 numbers, and our output might be the largest of the 3 numbers. It's displayed on the screen. So when we look at computer programs, we have a whole series of what inputs and outputs are. And I've given you some examples of embedded systems, the satellite, the accelerator on a car. The output of our Mama restaurant might be able to display on a cash register telling the customer how much they owe for their meal. Right there. That's an output of our system. The inputs, of course, are the little push buttons, for the waiter that they're, when they put the order in. So we have to look at what are the inputs to our system, what are our outputs, and how are they related to each other. Our computer program has to generate outputs that make sense for a particular set of inputs. Sometimes we have to look at our inputs and say, do they make sense? Sometimes people will input things to computers that don't make any sense right there. And we should ignore them, or we should come back and say, are you sure that you want 2 million nasi lemaks right there? Are you sure that's what you want right there? You might want it. I mean, if you're buying food for all of Clank Valley and out there, and you're buying it I don't know how long it's going to take your restaurant to fulfill that order, but out there. So getting back to our discussion here. Right there. All right, how do I... Here we go. Sorry about that. As I said, I've got a little bit of a sinus headache going here. So pseudocode they're not executed on computers. So we don't care about syntax, we don't care about location of semicolons, we don't care about keywords. All we want is something that is going to help us think through the problem. The whole goal is that this is a process of thinking, how are we going to do this? Right there. We start writing out the solution to our problem. Before we can write pseudocode, remember we have to understand the problem. Step number one is knowing what we're supposed to do. Step number two is kind of writing out the pseudocode is how are we going to do it? That there. And these are the two steps that make the great programmers from the poor programmers, is the ability to see what the problems are and to come up with a solution for it, right there. Steve Jobs was not a very good programmer. You know, but he was great at envisioning how to solve the problem. But he paid other people to write the programs, paid other people to design the hardware, but he was a great visionary in terms of how, what type of device do we need to solve this problem? The problem is people need a cell phone that does everything but make phone calls to that there. So they came up with the iPhone. I mean, before the iPhone, although the iPhone was actually a copy of something that the BlackBerry that was out before that there. But the the iPhone did it in a way that people enjoyed using it. That there, and I know people that have had BlackBerries and they loved them, but the iPhone was the device that everyone jumped towards and thought it was great. And then of course, another company came out. Google's a big company; they're a big player. They developed something, the Android operating system. And the Android operating system actually looks very much like the iOS operating system. They are, Apple's right. They copied it. Of course, Apple doesn't tell you that they copied it for somebody else. But the whole thing is that when we look at pseudocode, is you're attempting to write out there. And pseudocode also extends to hardware development. We can draw a little sketch drawing to what our building is going to look like. Where are we going to put the windows? Where is the air conditioning systems going to go? Where do we put the elevators? These are all drawn out, sometimes on the back of napkins at a restaurant between engineers. But this whole concept there. So now, this one here is carefully prepared pseudocode may be easily converted to corresponding C program. As you get better at writing pseudocode, your pseudocode starts looking more like C code. That there. Now, it may be still in Malay, but you can easily translate it to C. Now, C is a language based on English. Right there. So translating pseudocode written in English to C is obviously going to be a more automatic process than C code, pseudocode written in Malay or Mandarin or Turkish or whatever other language you choose to use. But pseudocode so pseudocode consists only of action decision statements. In other words, you don't put things in the pseudocode that if it's going to be part of the actual C code, that involve human interaction. In other words, your computer program doesn't pick up the food from the counter and carries it to the table. That's there. You just simply put in your pseudocode, display table number, above a certain place on the table that they're, what I'm envisioning here is here's the countertop there at your restaurant, and here's a little spot where they place an order right there. So there's some dishes here, whatever, and above here might be 39. And that's the table number. Here's another little partition. There's some dishes to be delivered. This goes to table 15, right there, and we display those numbers. Again, I haven't seen this in a physical restaurant, but that's one solution I might come up with of how I want to do this. Is I may have 3 or 4 places on a countertop, and above each spot there's a little place to display what table that order goes to. So as a cook prepares the order, he places it on the countertop and he pushes the button for what order. Again, I'm designing a restaurant. I've never owned a restaurant. I've never ran a restaurant. But I'm thinking, all right, this is one solution to that problem. I'm solving a problem. How do I get the food from the kitchen to the table? And that's, again, this is all part of that problem-solving discussion right here. She might think of a better solution. You might think of a better solution. He might think of a better solution. He might have a better solution. Which solution's right? I don't know. Sometimes you sit around in conference rooms with a big whiteboard and everybody presents their ideas and they discuss them. That's part of the design process that goes on in designing a restaurant. Sometimes it's the owner just does it by himself and he comes up with the crappiest solution and his restaurant goes out of business. Believe me, I've seen that happen. That there. But these are all things that you look at. As engineers, typically, I prefer to work with the group setting where you sit down and you discuss each of the various ideas, and maybe the final design that you work with may not be any of the single designs, but a combination thereof. That's part of that problem-solving technique. Is you get together with a group of your coworkers or friends and you discuss what the problems are, how do you solve them, and you outline different solutions, and you do it as a group. I don't know how many times when we've had problems at my old university that would need to be solved, that it was a Friday afternoon at the golf course and 18 holes of golf, and by the time we finished 18 holes of golf, the solution worked out. So not all problems are solved in the boardroom or at the desk. In this case, it was the golf course. Sometimes it's the Mamak restaurant at night. Sometimes it's the canteen. Sometimes it is 2 or 3 of you sitting in somebody's cubicle or office. Problem solving occurs everywhere out there. There's no one right way of doing it out there. So it does out there. But pseudocode converts over to C right there. And now this is in my pen just where, that is the weirdest thing. It was working 5 minutes ago, right? Out there. And now all of a sudden I'm drawing a line at the bottom of the screen and it shows up out there. What is going on here? Out there. Oh well. So I guess I can't use the pen right now. I was blaming it on the interface. I was blaming it on out there, but now it's just and it worked halfway through it out there. It works in OneNote, and now it still doesn't work here. So okay, well I broke the pen. The pen has got my sinus headache out there. Okay, so. When we write pseudocode, we write it thinking in terms of this is going to have to go into C. So we have to think in terms of doing adding, subtracting, multiplying, dividing, if statements, or statements. You tend to think like the computer when you write it, but you still have to write it out in steps. That there. Definitions are not executable. We will put definitions in there. There's only messages to the computer. So this is the definition, int I. Now, as you write your pseudocode, I typically off to the side, I just keep a list of what variables I need. Right there. I just write a list of any variables I need to keep track of. I just write them in a list right there. So that way I don't forget them, because if I'm using them in the pseudocode, they're going to have to be defined in the compiler later. There. So here we're talking about the difference between executable code and non-executable code. Int I is a definition. I'm defining I as a variable of type integer. I'm not doing anything with I. I'm just setting aside space for it right there. It's like going to a big plot of land and drawing lines on the land and say, this is going to be this address, this is going to be a street. I haven't built any streets yet. I haven't built any houses yet. All I've done is define where they're going to go. That there. So once I start the building process, then I have streets and addresses there. So nothing, by defining it, we don't cause anything. No calculations are done. Nothing's done. Now, sometimes, and this gets where it gets confusing, sometimes you can combine a definition with an executable. I could write a statement saying int I equals 10 right there. What I've done, and this is a bad habit to get into, many people do it, I define I as an integer and I initialized it to a value. So I've combined a non-executable statement, the int I, with an executable statement, I equals 10, right there. And as I said earlier, C is not my first choice for teaching programming, because C allows you to pick up a lot of bad habits, right there. So, that there. And believe me, programmers can pick up bad habits on their own without a language helping them. Just like drivers can pick up a lot of bad habits on their own. You could spend 6 months going through a motorcycle driving school, which I've spent enough time doing that, and they teach you all these technical skills on how to go drive across the beam and how to go around the cones and how to go around the circles that there. And then as soon as you get the license, you start running red lights and cutting through cars and doing all kinds of things like that. So you pick up the bad habits later. They didn't teach you in school. That there. Well, C allows us to learn bad habits while we're learning the language. So that there. So some programmers choose to list each variable and briefly mention the purpose at the beginning of the pseudocode program. I prefer that technique. Now, I don't necessarily have a comment for each variable. I usually try to use names of variables that make sense. In other words, if I'm doing a payroll program, I might have an employee number as a variable, employee name, first name as a variable, employee last name as a variable, employee pay rate as a variable, employee insurance plan is a variable. I mean, in other words, these are all variables that they're, so I don't have to write down / employee number. The name of the variable is employee number. It eliminates the comments and also makes the code easier to read. But it also makes it longer to type. So if you just use ENR for the name of the variable. It's only 3 letters, but then you have to remember ENR is employee number. If you just type out imp number and employee number as a variable name, then every time you see it, you know that that's employee number right there. Normally programs are, this is, and I'm running, I still have time because I started late up there. I said my headache's gone, but my sinuses are plugged there. But 99% of the code that we write as programmers is sequential code. It does one line at a time. Now we may transfer control, call a subroutine, and transfer the code. We may have loops where we repeat the instructions a number of times, but we only do one thing at a time right there. And that's what we're going to do in this class. We're not going to do anything up there. There are other types of programming where you can have parallel operations. 2, 3, 4, 5, 6, 8, 10 things are happening simultaneously. If you've got a i7 processor with 6 cores, that means that each core that's there. And when I talk about, now here's a processor right here, and we've got, I'm just going to show 6 here. We've got 6 cores each one of these. Each one of these cores is another microprocessor right there. So this processor can be running program X, Y, Z, A, B, C. We could have 6 simultaneous processes going on at the same time. Pieces of code. They may be part of the same program. They can be different programs. This could be running Word. This could be running Excel. This could be running, Edge, whatever the web browser is. This could be running part of the operating system. I mean, each one of these cores could be running a different program all simultaneously. Or they could be running different parts of the same program. We're not going to get into that level. That is a much more advanced topic than this course can address. It's multi-core writing software for multiple core processors, or writing parallel operations. I've worked in digital design where I would have, here's my chip, and I might have a part of the chip that does this. I may have another part of the chip that does this. This has some inputs, this has some outputs. Maybe some of these inputs go to this part. And these are all different circuits within the same chip. And I write VHDL code, and I run parallel processes. They run completely independent of each other right there. So we get this idea where we have concurrent processes. Concurrent means that they're running at the same time, or parallel processes, right? That there. You as a student, you do concurrent courses. You're taking 4 or 5 courses simultaneously. That there. If you're doing a sequential program, you would take one 6-week or 4-week module, then another 4-week module, and it would be a series of courses. So when we look at, we can do 4 things at a time, right here. These are all happening at the same time. Or we can do 4 things, one right after another, right there. So this is a sequential process right there, where we do one thing, we finish that, we start the next thing. Most relationships are sequential. We don't have, although in Islam, men can have 4 wives. Typically, it's not considered good to have 3 simultaneous boyfriends if you're a young lady, right? You shouldn't be dating 3 guys at the same time. But people do it. I mean, I'm not saying that they don't do it. You know, same thing with the guys. You shouldn't be dating multiple women at the same time, but some guys will do that. But sequential is what we're going to be doing. So there are various, the name will just specify what the next statement is. We'll be looking at if, we already covered the if, or we can skip a series of statements right there. So we do the if, we say if A is greater than B, do these things. If A is not greater than B, we skip those statements and we go on to the next statement after the if statement right there. So we do everything sequentially, but we have some control right there. So we have control there. We may have where we call a function and do a series of instructions within that function. That there. Where again, we're transferring control. Right there. We're still doing one thing at a time. Right there. So when we write programs in this course, this semester, everything is sequential. Right there. Now we have transfer control, but we do it in life. Things may not be sequential. Right there. You look on an aircraft, the computer that controls the jet aircraft, the engines on the aircraft are controlling four engines simultaneously, and they may be doing different control on each of them. You know, they may be setting one to one speed, one to another. They may be making adjustments. At the same time, the rudders and the flaps are being controlled. These are all being done simultaneously by different processors in the system. You have different parts of the aircraft that need to be controlled. The heating and cooling system, most planes don't have heaters in them, but they definitely have cooling systems, or don't have coolers. Yeah, they do now. Most of the time it's the heaters that are running, because when an airplane's flying at 30,000 feet, the air is pretty cold out there. So, but when we look at hardware, quite often we have multiple processes that are running simultaneously. Sometimes we have to make them look like they're running simultaneously. In reality, they're running. So here in the 60s, it became clear that indiscriminate use of transfer was the root of. Oh, yeah. There used to be a statement at one time that there used to be a statement called the go-to XXX statement right there, where we can just tell the program to just go someplace else in the code. And the old go-to statement was the root of all evil when it came to programmers right there. So that's what he's talking about. Became clear, indiscriminate transfers, great deal experienced by so we don't see the go-to statement anymore. We'll see the call, or we call a function. It goes through and runs the code, and then it returns back to where it's called from. Or we see the looping statement where we loop, but we don't use the go-to as much as used to, right there. Favor or blame was the go-to statement right there. Notion of all structured program came almost synonymous with the go-to elimination. So, in other words, you won't see the go-to statement. That was a statement in both Fortran, Pascal, Fortran and BASIC, COBOL. It somewhat disappeared in Pascal and was never part of C as a general. It still exists, but we just don't use it. Right there. Right there. Results were impressive. As the go-to went away, programs became clearer and easier to debug and a lot less problems. And we will have to say that computer programs today are much, much more reliable than they were 30 years ago. The techniques of developing software is much, much easier. The tools we use are better, they're faster, and we get much better code today than we ever did back 30, 40 years ago. On the flip side, what we're asking our code to do today is much, much more difficult than what we asked it to do. When I was a young student taking Fortran as my first computer programming language on punch cards, my longest program was probably 30 lines. Because it took hours and hours and hours to develop a 30-line program and to get it to work properly. Now I can give you a program that's 200 lines and expect you to crank it out in 2 days. And if you're an experienced programmer working for Google or Amazon or any of the big companies, they're expecting people to crank out 10, 15, 20 pages a day of code that works. Right there. So what we expect computer programs to do today is much, much greater. Same thing with computer hardware. Back 30, 40 years ago, 64K of RAM was considered a big computer. Now that's not even the tiniest part of just your cell phone memory. I mean, most cell phones have got 1, 2, 3, 4 gig. I think your cell phone's coming out with 6 gig of RAM. So control structure, sequence structure, structure selection, iteration. These are all the terms that they're not so much worried about. Programs using structure techniques, and my pen I know won't work here, but I can use the mouse right here. Structured programming techniques were clear, easier to debug, modify, more likely to be bug-free. So structured programming was developed as a way of being able to write better code faster and more reliably. The old way didn't work. I learned the old way. That's the way I learned 40 years ago. That's it. So flow charts, I'm going to skip flow charts, and actually I think you'll still see flow charts where we graphically show how things are. I haven't used a flow chart in years. I'll refer to them occasionally in this class, but we used to, when I first learned the program, we bought this little plastic template that had circles, ovals, squares, hexagons, various things. And we used that to draw flowcharts for all of our programs. And we did a flowchart for every program. But remember, back then, we had to write our code on paper, and we used a coding form where we put, comment. If you wanted a line to be a comment, you put a C in the first column. If you wanted a line number, it's the next 3 columns. You started the code, the actual instruction on like the 7th column or something. But you had all kinds of restrictions on how these cards had to be printed up. So we did a lot of manual work before we started coding. And one of the manual jobs was to do a flow chart for each and every program. I'm sure this flow chart is probably from Dad. He probably insisted it be left in there. Most programmers don't do flow charts for simple programs. Now, for more complex systems, they may do a flow chart for the overall system design. But you would not write add, grade to total in a flow chart. You might do that in the pseudocode, you might do that in C code, but you're not going to do it in the flow chart right there. So this just talks about flow charts right there. And now we're going to get back to our structures out there. And I think now is probably a good time to call it a week. I'm still at an hour. I keep saying that my normal is 1 hour, and there's something about my internal clock says that I'm done out there. So